Hello and welcome back to the third week of the Operations Research 2 course. So in the previous 2 weeks, we have solved some optimization problems using dynamic programming approach, and we have also seen sometimes the formulation of the recursions. This week, however, we are going to focus on formulating the recursions. So not really on solving the problem itself, like getting the answer that the total cost is 1,200 or anything. So we don't really deal with the exact numbers, but we are going to have, let's say we have T periods, and then the demand for the period T is dt and so on. So basically we're trying to generalize the problem so that we don't have the exact numbers, but we have the notations. So that's why we're going to focus on how we are going to create the formula for the recursion such that we may create a recursion that works for a general problem. Let's say we have T periods, T maybe one is not possible. Like we have, let's say 5 periods, 10 periods, 18 periods, then it's the same recursions actually. The formula is the same except that we have T from either 5, 10, or 18. So that's why this week we are going to focus on the formulation. So let's start. So in general, the recursion function looks like this. So remember that in dynamic programming, we divide the problem into stages. So the cost from stage T until the end of the problem, we break it into the cost during the stage T itself plus the cost from the stage T plus 1 until the very end of the problem. Okay? And there are three aspects that you always need to think about carefully and then define them carefully and explicitly in your recursion. The first one is the set of allowable decisions. So let's say you are now at city I. What are the possible or allowable decisions city J that you can go to? That's an example. Okay. And then the second one is the aspect 2, how the cost during the current stage. So this is aspect 2, depends maybe on the value of the T, the stage, the current state, I, and then the decision chosen at the stage T. And then the third aspect is this, how the state at the stage T plus 1, so how this new state depends on the value of the maybe depend on the value of T, the state at stage T, and the decision. Usually the biggest influence comes from the decision. So how your state changes from I to become the new state at the stage T plus 1, usually it is largely influenced by your decision at this stage. So let me illustrate those three aspects using the last example that we've seen in the previous week. So this equipment replacement problem is from the last video in week 2. Okay, so the first aspect is whether we can trade or keep the machine or only trade the machine. So it depends on the age of the machine in that example. If your machine is 2-year old, then you may either trade or keep it. If your machine is already 3 years old, then the only allowable decision is to trade the machine. So that's the aspect 1. And then the aspect 2 is all the cost, revenue, and everything that happens at this stage. So here it depends or is affected by your decision and the current state of your machine. Let's say the current state of your machine is already 3-year old, you must trade that machine. So you get the salvage value, you need to purchase a new machine, and this is the maintenance cost. Everything is affected by the fact that your machine is already 3-year old and you must trade that machine. Okay, but main point of aspect 2 is all about this stage. So all about stage T. While the main point for aspect 3 is that it's all about the stage T plus 1. So here you can see that the age of your machine changes from 2 at time T to become 1 at time T plus 1 because it is affected by your decision to trade the machine. So you trade your 3-year-old machine, buy a new one, so then next year the age of your machine is already 1 year old. Okay, so aspect 1 is the allowable decision, and then aspect 2 is the cost or revenue at stage T, and then aspect 3 talks about what happens at stage T plus 1. Now let's see an example. In this example, the owner of a lake must decide how many bass to catch and sell each year. So bass is the name of a fish. Okay. And then you see there is a revenue from selling the fish. There's also the cost of catching the fish, and the cost is a function of how many you catch. So it is a function of X, the number of fish that you catch, and then B is the number of bass at the beginning of the year. Okay, and then what the owner of the lake wants to do is to maximize the owner's profits over a T-year horizon. You may pause this video to really read this problem carefully before you continue. Okay. So before we really formulate the recursion function, what we need to do is think about all these three aspects. So the first aspect is talking about what are the allowable decisions. Remember that in this problem, your decision is to decide how many bass to catch and sell each year. So aspect 1 says, what are the allowable number of bass fish that you can catch and sell each year? Well, it is quite logical. If you have B number of fish in the lake, then you obviously cannot catch more than B fish, right? Let me repeat. If you have B fish in the lake, then obviously you cannot catch more than B fish. So here, the aspect 1 may be written like this. XT is the number of fish that you catch at the year T. It must not exceed BT. So it is less than or equal to BT. BT is the number of bass in the lake at the beginning of year T. Okay, and then you also cannot catch a negative number of fish, so that's why here X must be greater than or equal to 0, or in other words, 0 is less than or equal to XT and XT is less than or equal to BT. So this is how we write that the allowable decision for XT in every year looks like this. The aspect 2 talk about the cost, the revenue, and everything that happened during the year T. Because here it says we want a recursion that maximizes net profit. So in aspect 2, we've tried to formulate the net profit during the year T itself. Okay, so during the year T, if we catch, let's see what we do during year T. We catch the fish and then we sell it. So the profit comes from selling the bass, which gives us the revenue of RXT minus the cost of catching those fish. So the cost is CXTBT. So it means that the cost is influenced by how many fish we catch and also by how many fish are in the lake. Okay, so the net profit of the year T equals R xt minus C xt bt. And by the way, we don't really care how this function look like. So it may be, let's say, 2xt minus bt or 3xt minus 0.5 bt, or it can be whatever. Okay, so don't be confused with this, and we don't care how the function looks like. We just say that the cost of catching xt fish is c xt bt. Okay, same thing for the revenue. We don't really care how much we get from selling xt fish, maybe like 100 times xt or 150 times xt, whatever, but we just write down the function as r xt. So in aspect 3, we care about how the state would change during the year t plus 1. So the main point is about t plus 1, and specifically it's about the state. Okay, so at the beginning of this year you have bt fish, and then after the activities that you do catching the fish, we would like to define how many fish you will have at the beginning of the next year. So here you start with bt fish at the beginning of year t, and then you catch xt fish. So it means at the end of the year you will have bt minus xt fish, right? bt at the beginning, you catch xt of them, so at the end of the year you have bt minus xt base fish in the lake. However, the problem says that at the end of the year, like at the very midnight of December 31, 20%, suddenly your base fish becomes 20% more. So in other words, this is the base fish that you have at the end of the year, bt minus xt. So at the beginning of the next year, suddenly it will be multiplied by 1.2. Okay, so remember that 20% more here means that your fish is multiplied by 1.2. Remember, it is not multiplied by 0.2, but you must multiply it by 1.2. Because the existing fish is still there, and then you get 20% more. So the multiplier must be 1.2. Okay, so at the year t plus 1, the state will become 1.2 times bt minus xt. So 1.2 times whatever remains in the lake at the end of year t. Now, after we have thought about all the aspects, let's start formulating the recursions. Usually we separate the recursions into stage big T, which is the very end of the problem, and then the stages small t. Let's start with stage big T. So this is the very last year of the problem. We have bt fish, and then we get the revenue from catching xt fish minus the cost. So you don't have ft plus 1 here because big T is already the end of the problem. Okay, let's see all these notations one by one. So RTXT is the revenue from catching xt fish, and this is the cost from catching those fish. Remember, it is a function that depends on how many you catch and how many there are at the beginning of the year. And then here you have the curly bracket, and then you write down xt here, means that among all possible values of xt, among all possible values of fish that you can catch, we would like to find the one that gives us the maximum net profit. Okay, so imagine you may catch 0, 1, 2, 3, 4, 5 up to BT fish, and here the curly brackets means that among all those possible numbers, we would like to find the one that gives us the maximum profit. So FTBT is the maximum net profit from the year T until the end of the problem, if at the beginning of the year T we have BT fish. Okay, and then this is the allowable decision that you may catch the fish from 0 up to BT. Now let's move to the previous years before the big T. So you can see the T is small. So FTBT is the maximum net profit from year T, T is small, until the end of the problem, if at the beginning of year T we have BT fish. Same as before, this is the revenue from catching XT fish, and that is the cost, which depends on both XT and BT. But now you must have FT plus 1, right? Because FT means the net profit from year T until the end, and then this is about the year T itself, and this is the rest, such that we reach the end of the problem. Now here you see that the state changes from BT to become 1.2 BT minus XT. Remember, this is our aspect tree, which says that we have BT fish at the beginning of this year, we catch XT of them, but then at the beginning of next year, that number will suddenly be multiplied by 1.2. And then same as before, we say that among all possible values of XT, among the all possible values of fish that we can catch, we would like to find the one that gives us the maximum net profit. So just a short illustration about aspect tree. Let's say you start with 5 fish, so BT equals 5, and then you catch 2 of them. So at the end of the year, you have 3 fish remains in the lake. But then at the beginning of the year, this problem says that it is suddenly multiplied by 1.2. So at the beginning of next year, you have 1.2 times 3 fish. So here's the summary of all the things that we have defined. The stage is year from 1 to up to big T. The state is the number of fish at the beginning of the year, T, which is denoted by BT. And then the decision at each year is how many fish we catch, which is denoted by XT. And then here's the recursion for year T, big T. And then this is the recursion for year small t, which is less than big T. And do not forget to write down the allowable decisions for each of the recursion, for the year T and the year small t. So for the same problem, if you would like to incorporate time value of money, which says that the amount that you receive next year equals to the amount that you receive this year but smaller, like I give you $100 next year, maybe it is, you say it is equal to $92 today. So you multiply FT plus 1 with a beta multiplier, and beta is less than 1. So using this way, you already incorporate the time value of money. So that's the end of this video. You have seen how we may formulate the recursion function to a problem that do not have numbers on them. Like we only have T periods, the revenue is RTXT, and then the cost is CXT/BT. So in the next video, we're going to look at different types of problem, and the same thing, we're going to formulate them into recursion functions. By the way, I suddenly have one question to ask. So this is the recursion for stage big T. Since big T is the very last period in the problem, why don't we just catch all the fish in the lake? which would make our recursion look like this. Why this is, I wouldn't say this is wrong, but I would say why this is not very correct for this problem. Okay, so thank you.